Hi, welcome to lesson 19E, regression of line of x against y. Usually we'll find the equation y equals mx plus b or ax plus b, where it's the regression line y against x, where x is the independent variable and y is the dependent variable. We have been told in the past that the x is the explanatory variable. That's what the other variable will depend upon. So the x is the independent, and the y value is the dependent, also known as its response variable. So it's response, I guess, because it depends on the independent variable. So now we're going to take a look at situations where perhaps the independent variable isn't as precisely known as the dependent. A lot of times, suppose we're looking at, like it says here, height of a plant as it grows over time. The time we would know, because if we're looking at, say, a tree growing over a certain amount of time, we know the amount of time that we're looking at this tree growing, and then we can determine the height of that. If it's the height of a plant, for example, with the amount of water that it receives, we know the amount of water that we're putting in. We can be really precise about that if we wish, and then we can measure the height of the plant from there. So if the independent variable or the explanatory variable is precisely known, then we can use y against x quite easily. If, on the other hand, the explanatory variable, the x, isn't known precisely, then sometimes it's better to reverse the x and the y. So we would find the regression line of x against y. And in cases where that would come up would be if we're dealing things with time, like the example in the lesson here, painting business, people are painting for a certain amount of time, they get paid per hour. But even if they work maybe a couple of minutes short of an hour, they'll still get paid for the full hour. But it's not a specific amount of time that they're actually working that we're examining. For example, also maybe the length of time that somebody's working on their shift in a fast food restaurant. They may be scheduled for a 3-hour shift. They might work for 3 hours and 5 minutes, but they'll just get paid for the 3 hours. So we have to kind of take a look at that, and if we know the value of the dependent variable, that would be more precisely known than the independent. So usually, like I stated above, the line of best fit is y against x, written as y equals ax plus b, but we can turn it around. X against y would be x equals my plus c. So there is a long, well, fairly long, in-depth way of determining this algebraically. But what we can do is we can just use the GDC, and we can find the linear regression without really knowing what's going on, and we can actually figure out the values that we need. So in this example that we're looking at, we've got amount of time some families are spending preparing homemade meals, and then the amount of money that they spend on fast food. Well, even if they say that they're spending money, or they're spending 3.5 hours on a homemade meal, would it be exactly 3.5 hours? Could it be maybe 3.6 hours or 3.45 hours, etc.? That 6-hour meal preparation in that next week, maybe that's 5.7 hours or 6.1 hours. So the time isn't going to be exactly precise. Whereas the money that they spend in fast food, that's, I mean, you get the receipt and you know, okay, I'm spending $85 on fast food that week, or $60 on fast food that week, kind of thing. So the amount of money that's spent on fast food is precisely known, whereas the length of time preparing homemade meals is not going to be specifically known. Okay, so that's why the regression line of x against y would be more appropriate in that case. okay, because it's more the dependent variable or the response variable is the more precisely known than the independent or the explanatory variable. Okay, so we want to find the regression line of x against y. So if we use our graphing calculator, I just have to share that with you. And okay, so I've already put in the values for the top row of the table of values in L1. So 3.5 hours preparing a meal, 6 hours preparing a meal, 4 hours, etc. For those weeks. And then L2 is the amount of money spent on fast food in each of those weeks. Okay, so I just put the values in. I go to second y equals, the plot is on, so I'm going to go in there and see what's happening. And now usually what I would have, so it's on, I'm choosing a scatter plot. The X list is usually L1 because that's the first column in the table of values, and Y list is usually L2. But this time I've reversed them. And so if I were to graph this, okay, I've already graphed the line as well, but here's the graph of the scatter plot, and there's the line. And I'll find I'll do the linear regression of that to show you how that works as well. So the X list in the linear regression is L2. The Y list is L1. So I've reversed it again the same way as I did for the scatter plot. Frequency list, we're just going to leave blank. When we store the required or the regression equation, I'm going over to Y vars. So I hit vars and then Y vars, and then I'm doing function, and I'm going to store it in Y1, and then I calculate, and then I see that the A value or the gradient for this line of x against y is negative 0.05759. And the y-intercept, B, is 8.29. And the R value, not that it's necessary in this case, but it's helpful to kind of see. The R value is negative 0.87, meaning, of course, it's a negative correlation. So the line is sloping down towards the right. And 0.87 is a fairly high correlation. Okay, so it's a good fit here. Okay, so now the next question says, use the regression line to estimate the time spent preparing homemade meals by each week by a family that spends $45 on fast food each week. So if I go to the graph, I can hit trace, and then I can put in 45. Can I do that? Nope, sorry. Let's try that again. Trace. Okay, so that's I'm tracing along the points. I want to now trace along the line. There we go. So if I can find 45, there we go. Okay, so that's the line. So when X equals $45, and now that's the amount of money on fast food, they're going to be spending basically 5.698, or approximately, I'd say 5.7 hours on fast food. Or sorry, 5.7 hours in preparing meals. And I'll just write that on the smart file, which I'll show you in a couple seconds. And then if we say the amount of money spent on fast food each week by a family that spends 5 hours each week preparing the meal. So I'm going to trace along here. And I'm going to be tracing the line. And I want to go to y equals 5 hours. And so I'm going to go down. So 4.96. Actually, maybe I'll zoom in also to get a little bit closer. I can get a bit more of an exact amount here. So if I hit trace again, I go to the line and I want to go to 5 hours. and there's 5.006. So, okay, that's pretty close. So if they spend 5 hours a week preparing meals, they will be spending approximately $57 on fast food. Okay, and I'll just change the sharing. So by using the trace feature and switching from the scatter plot to the line that was on the window of the TI-84, we found that if somebody were spending $45 on fast food, they would be spending about 5.7 hours in meal preparation. And if they spent 5 hours on meal preparation a week, they'd be spending about $57 on fast food. Okay, so we can use the regression and the graph just the same as we did if it were y against x, as it is that we just did here in x against y. Okay, so that is the lesson 19E. So thanks for watching, and we'll see you in class.